Let me start by saying this is quite an honor to kick off this seminar series of our CAD workshop. And I also have to say, after that masterclass of the workshop of last week, I feel this is quite a tough act to follow, so I won't even try. This is going to be light and fluffy. Don't expect any Schottky Klein prime functions. Don't expect Riemann-Hilbert problems, nor exotic conformal mappings. This is going to be mostly pictures and speculation. Okay, I volunteered to give this first talk because I had a talk readily prepared. This is the one I gave in Valencia at the IKEA meeting in July. The slides are identical. I haven't changed those, but I've added some material for those of you who've been to that talk. I've added material that I've been working on the last few weeks, including here at the Institute. And so I will talk about that. I will be also showing animations that I didn't have time for in Valencia, which means that I will probably not get to the numerics at the end, which is a pity. And that we can schedule that later, or we can talk informally. So, what is the plan? The plan is to start with these well-known differential equations, burgers, two flavors, KdV, and the new stuff that I'll be adding is KdV's lesser known cousin, the Benjamin-Ono equation. I'd like to add that to this list. It's not on the slide yet. And we're going to solve them on the same interval, using the same initial condition, and then see how the solution evolves. Now, those of you who know these equations will know exactly what's going to happen if we start them off with maybe just a sine function as initial node. Everyone knows how that's going to go. But what's different now is we're going to look at this from a slightly different angle, and that is from the complex plane. Now, I don't need to convince anyone in this room about this statement, and that is, if you look at a function only on the real line, you only get half the picture, right? And when you go into the complex plane, you get the full picture, and this is the reason why we're going to take a slightly different viewpoint of these equations, not just looking at what happens on the real line, but also what happens in the complex plane. Tied to that are these nonlinear equations have these nonlinear features, right? Solitons, shocks, finite time blow-up, recurrence, and we're going to try and link the complex behavior, the behavior in the complex plane, to these very typical nonlinear features of these equations. Okay. Right, let's start with, in this case, Burger's equation. This is something that everybody knows. We're going to start with the minus sign of x. The reason is simply, for the minus sign is simply so that we have the shock occurring at the origin and not at the edges. So we all know what's happening. The waveform steepens until the shock forms at time t equal to 1. And this can all be explained by characteristics. We can predict the time of breaking, etc. But instead, we're going to look at this from the complex point of view. This is not my idea. Many people have done this, and I'll mention some other names later. Okay. Where did this all start for me? A long time ago, in the late 1990s, and maybe I should give some history here because I know many people here know Greg Baker. What happened was, in the late 1990s, there was a joint meeting of the American Mathematical Society and the South African Mathematical Society in Pretoria, South Africa. Greg Baker and I were both expats, both at OSUs. He was at Ohio State, I was at Oregon State. We traveled to South Africa to attend this meeting, and he showed me this paper, and I've been looking at this ever since. So it's funny how life works, right? We were both living in the US, two South Africans meeting in South Africa, and influencing each other's research. Since then, I've been working in other things, but because when this invitation to speak at Valencia came up, I thought it would be nice to return to this particular topic because it appeals to a broad audience, I hope. And it's also colorful, as you will see. So I thought this would make a good topic for a talk in Valencia, and that's at IKEA, and that's what I did. So basically, this is where it started for me. This paper by these two French, I think they're physicists, they analyzed the Burgers equation, and not with a sin x initial condition that we are planning to do, but with a cubic initial condition. You see that the general shape is the same. They showed that, well, as time evolves, the profile steepens, just like in the previous slide, and there's a breaking. But they showed that the mechanism in the complex plane is the existence of a complex pair of branch point singularities that travel along the imaginary axis and then reach the imaginary axis at the time that the shock occurs. And I thought this was fascinating, and I wanted to compute it. And that is where my interests lie, how to compute these things numerically and stably. So I'm not so much interested in the theoretical side of things. I'm interested in the numerics. Okay, so other than that, we have roughly the same situation. We don't have the cubic equation. I prefer our sine of x because at least our sine of x is bounded. This one is unbounded, so it doesn't really model anything. So let's return to our sine of x initial condition. We're not going to do hand-drawn pictures. We are going to use wonderful software, and we have the creator right here in the audience. It's Elias's book and software that goes with that, the visual complex functions. So we're going to represent complex functions as follows. Elias calls this the analytical landscape. So you take your function and you write it in polar form, and then the height represents the modulus, and the phase is given by color, right? So if you have a pole here, of course, the modulus blows up at the origin, and you can even see the multiplicity of the pole because the colors go around twice, the phase runs twice. If this were a zero, for example, the colors would simply just run the other way, and so on. And here we see the typical jump in phase along the branch point, branch cut of something like the square root function. And this is the color wheel that represents the phase, right? I don't think I need to explain phase plots to this audience, but there you go. This is what we're going to use. And we'll be looking, when we solve our PDEs, we'll be looking at identifying poles and branch points in this way. Right, so first off, let's start with our implicit Burgers equation. By the way, that equation as it stands there has an explicit solution in terms of a Fourier series, given by Platzmann in the 60s. But even though you have an explicit Fourier solution in terms of a Fourier series, you cannot really do much with that numerically in the complex plane. Because the moment you go into the complex plane, those signs start growing exponentially, and that just kills you. So you cannot use that really for practical computations. So instead, what I did here was just to take the implicit solution formula, which we have for the Burgers equation, and solve it numerically. Consider it a transcendental function in terms of u. And MATLAB is nicely vectorized, so you can take this x to be just a chunk in the complex plane. So you start off with the initial condition, f of x, then you increment time by a small amount, then you do Newton iteration until convergence, then you use that as initial condition, increment time, again, do Newton iteration, and this is how these pictures were generated. So this is small time, nothing really. Maybe we should look at the dark curve here. That is just the the same picture, the same curves that I've shown here, but now in three-dimensional space. Right, so we see the steepening of the curve as time goes on, and then the breaking as the shock forms here at time t equal to 1. Now, what's different now is we're looking in the complex plane. There's up-down symmetry, so we're just looking at the upper half of the complex plane, not the lower half. And then as time goes on, we see a branch point entering here. If the colors are good on this display, then you can see that there's no jump in phase in front here, but at the back there's a jump in phase. And if you look at the colors more carefully, you'll see that that looks like a square root singularity, and you can corroborate that by theoretical analysis. So this branch point comes in, it moves down, same as in the Bessie and Fournier paper, and then it matches its other half that came from the bottom, and they reach there. And the moment they reach there, this quadratic singularity turns into cubic. It becomes a cubic singularity. Actually, Mark has some very nice pictures of the Riemann surfaces that goes with this. You can do just a regular singularity analysis, and you can find the precise point of the branch point, the precise location of the branch point, and you can classify it, etc. The two French people that I mentioned, they continued beyond the shock. It becomes quite complicated behavior on the Riemann surfaces. But let's continue now. Let's add some diffusion. So we go to the regular Burger's equation, the one with a small amount of diffusion. And we all know what's happening here. We have the same steepening of the front, but diffusion prevents the shock from forming. And we have this very typical, almost sawtooth-like shape that just then collapses to the steady state of 0. If you look in the complex plane, the branch point singularities have collapsed into a string of poles, right? So you lose the branch point, you get poles. The poles advance along the imaginary axis, but they don't reach it, right? There's no breaking in the solution. And eventually the poles reverse their direction. This is what it looks like. You have the poles coming in, getting to a minimum distance here, and then turning around and walking back out. And what you have here is just the location of those 5 poles as a function of time now. So you can see them coming in, reaching a certain minimum distance, and then going back out. The initial onset is quite fast, right? They have to come all the way from infinity, so they zoom into, and then they turn around and sort of slowly back out. And I'll show you an animation shortly, which is something I didn't do in Valencia because of lack of time. This dashed dot curve here is the location of the branch point singularity in the case of 0 viscosity. These curves don't start there. They should be asymptotic to the dashed dot curve, but it becomes very difficult to compute in this area because of the proximity of the roots. So it's an ill-conditioned process to compute there. So what do we know about analysis for this case? Well, pretty much everything. There is this Hopf-Kohl transformation that most of us are familiar with. You take the Burger's equation, you linearize it by introducing a substitution, something like a logarithmic derivative, and you turn the nonlinear Burger's equation into the linear heat equation. You have to transform the initial condition similarly, and then if you can solve the heat equation, and you can with Fourier series, it all boils down to just, this is our initial condition, We just need to find the Fourier coefficients of this function, and we know those explicitly. Those are the Bessel functions, and so that's how that series was derived. So I was happy to see that this is an exact example in the original paper of Cole, right? The sign of x initial conditions. It comes directly from Cole. That's the reason I like the sign of x initial condition. It ties in all these historically important papers. Right, so that's what one finds in Cole. You can compute with this, but especially for small values of t, this is not so great. And then for theoretical analysis, maybe the integral representation that one finds in Hoff's paper is more useful. So, for example, if you want to predict the locations of those poles, you can just look at the denominator here. You can figure out what this f is. This is just becomes integral of minus sine of x. You can do that. And then you do a saddle point analysis on this. And if you do that, you can predict the locations of these poles that I just showed you. You can predict them very accurately. So analysis there, again, is in check with the numerics. Right. Okay, what I wanted also to point out is lots of typos those days. This is a snip from the Cole paper. You'll see there's a new squared. One of them is wrong. There's an N naught. There's a U naught. One of them is wrong. And so it goes, the entire paper. But apologies to those of you who've seen this before, but that's nothing compared to this. This is Hoff's paper. The mu is the diffusion coefficient. The u is completely absent. I speculated that that these two guys knew about each other and they wanted to get their papers out as quickly as possible. So proofreading was not really the main thing. Anyway, one thing that I've added was an animation of the pole movement, and I think I'd like to show it to you, since this is an informal seminar, and if I don't finish everything in time, that's fine too. So there you go. Let's see. Okay. So here is the Burger's equation and the animation of the pole. So what I should explain is, I haven't really discussed my numerical method, but what it boils down to is solving the PDE using a Fourier spectral method, right? That is converting everything to Fourier coefficients, getting a big dynamical system in terms of Fourier coefficients, then integrating in time. That I pre-computed and saved. And then now at each time, I take that solution on the real axis and continue it numerically into the complex plane and plotted it with the software. So the numerical solution of the PDE on the real line was done a priori, and just the numerical analytic continuation is happening in real time.
What did you do to improve around the first?
No.
Because it blew up.
Of course, it blow up. So you have to limit the region.
And also computed with high precision.
Actually, this was just straightforward MATLAB. So you'll see some, not in the Burger's case, but in the next one I'll show you, you'll see some instabilities that I hope I can still resolve. So this is Burger's, right? So there we see the poles running from coming along the imaginary axis. What I didn't tell you was you can also model the pole behavior by a dynamical system. It's name I associate with that is Calogero. And if you look at that, there's a certain repulsion between the poles. So the one that comes from the bottom, I think, is the one that stops that one from reaching the real axis, the sort of repulsion, and then they start going back out. Right, it's almost finished. Yeah, so there was no high precision. This is just MATLAB, straightforward IEEE arithmetic. Okay, now, maybe I should, what I didn't say was I do the numeric analytic continuation by Fourier Padé methods, right? So it's not continuing the equation, using the Fourier series to continue. It's converting to Fourier Padé, and then it goes into the complex pair. Question now, what happens when we add dispersion instead of diffusion? Dispersion also prevents breaking of the shock, right? There's no shock wave in KDV or any of those things. What happens? And I'm going to show you in a second. I'm not going to do KDV because KDV is very hard to compute stably. I'm going to take its lesson on cousin here, the Benjamin-Ono equation. So this is this is KDV, the third derivative dispersion. This is Benjamin-Ono, the Hilbert transform of the second derivative. Now, everyone knows what the Hilbert transform looks like on the infinite line. There's a convolution with a Cauchy kernel, but this is on the periodic domain. I hope I said that initially. Everything in here is 2 pi periodic. And then it becomes a convolution with a cotangent kernel that I won't even try to write down. I think it's simplest if I just explain what happens in Fourier space. So in Fourier space, if you take 3 derivatives of a Fourier series, you just multiply by IKQ. What the Hilbert transform does is multiplies by IK squared, but that's just pure E equation. So you have to convert that into an odd function by multiplying with a sign, and to make these things the same, there's just a minus I here. So that's what Benjamin-Ono does. It's just a dispersion relation, as it's called. In KDV, depends on KQ, whereas in Benjamin-Ono, it depends on K squared. So the dispersive effects are less severe in Benjamin-Ono. That makes it slightly easier to work with. Okay. John, you?
No.
Oh, it's
Very happy about that.
you're happy. Okay. Right. So we're going to do that same picture now with Benjamin-Ono. You will see a little bit of instability in the beginning, but eventually things settle down nicely.
I was just puzzling about the singularity, the origin, the discontinuity.
Yeah.
Okay, I was just puzzling. I know that's in the integral as a singularity, and it's going to appear here in your formulation. That's all I was thinking.
Okay. So let's do Benjamin-Ono. Again, I preload the solution on the real axis. The analytic continuation is done real time. Okay, let's hope for the best here. So same story, the poles will come in from the imaginary axis, but they don't stay on it, they drift off because of the dispersion. And so the shock is prevented, but the mechanism is different, right? Because those oscillations that appear in the Benjamin-Ono equation, which I will call solitons, and then Mark Abelowitz will call me a physicist, right? Because I call everything a soliton. But these are all in the same class, these equations. Benjamin-Ono is also completely integral by inverse scattering, etc. So each of those solitons correspond to a nearby pole. Some of these are moving to this way, some are moving there, and then there's also some movement into the upper half plane. It's especially interesting when you have soliton interactions such as those. You have this bumping of each other in the complex plane. I still have to study this a bit more carefully. If anyone knows more about Benjamin-Ono dynamics, please. Here's another interaction. in the mid-1970s, Krosko said that soliton motion should be understood in terms of a parade of poles. Those are the words he used. And that's your parade of poles there. It only goes up to time 12 and we're done.
So you've got elastic collisions here.
Say that again.
You've got elastic collisions, as expected in an integral system.
Yeah, yeah.
So how, with which accuracy are they elastic?
I don't know. This is work of the last week or so. Okay. Now what are we doing for time? Right. So I was happy to see that BO Benjamin Ono I could compute relatively stably. You will see there were some instabilities. Now KDV. KDV is the same thing, right? You start off with our sign initial condition. You have the oscillations forming. And if you look at it very carefully, this is actually the original experiment of Zabusky and Kruskal where the soliton was discovered. I just had to fix that dispersion parameter, that mu, that I previously just had as 0.1 arbitrarily in all the other experiments. I had to fix so that it is exactly the Zabusky-Kruskal picture. Of course, for some reason they did it from 0 to 2. Why 2, I don't know. But I just converted all of it back to minus pi so that it matches all our previous experiments. Okay.
Maybe it was normalized by pi.
I don't know. But anyway, I'm pretty sure it's the same picture. As far as I know, I haven't seen these poles computed in the complex plane. And that's one of the reasons I thought I would pick this as a topic for the EPM talk, because I thought that would be a nice experiment to try. And it turns out it was way harder to compute than I thought. Not the solution of KEV, of course, that's simple, but the extension into the complex plane. I'm not going to show you an animation because it's still very unstable. Not very, but too unstable to show. So you have the same sort of business like previously. You have the singularities running in from the imaginary axis. They veer off, they drift off, same as in the Benjamin Ono case. And then they line up pretty much same as in Benjamin Ono. So this is the Zabusky-Kruskal, that iconic picture from Zabusky-Kruskal when looked at in the complex plane. So at least the 8 solitons that they've identified here can be identified fairly closely here. 1, 2, 3, 4, 5, 6, 7, 8. But now there's some other junk at the back, and I don't know what those are. When I read papers like the Biondini one that I just mentioned there, I see that people have claimed that there are more solitons in the Zabusky-Kruskal experiment than just the 8 that they've labeled. I've seen numbers like 10 or 14, even 14 solitons. What I don't know is whether these at the back are those hidden solitons, as they are called, or whether those are numerical artifacts. And that is something that I still have to have a look at. But you will recall that in the Benjamin Ono, it was a fairly regular motion, right? The poles came in from the imaginary axis, they drifted into the left half plane. Okay, then they entered in the right. Did I say that? They entered from the right because of periodicity. Maybe I didn't say that. Here it's not so simple. For example, if you look here, maybe the colors are not so great. You see, when they come in from infinity, they are poles of single multiplicity. When they end up in the Zabusky-Kruskal picture, they're poles of double multiplicity, and that's consistent with traveling wave solutions in the periodic case have a form of sigmoidal square, and those have poles of double multiplicity. So what happens in between? I conjecture what happens in between is that there are pole coalescences, right? Poles of single multiplicity meet up and create poles of double multiplicity. This is the best suggestion I have from an actual computation. But it's a complicated dynamic, right? It's really complicated to watch, and I don't really understand what's happening here. So it's not really a parade of poles. It's more like, in this country, more like Morris dancing, right? It goes around a pole, something like that. So it's quite complicated. I challenge a few people here to make the problem, let's make the problem simple. Let's make the problem real simple. Let's do the infinite line, okay? KDV on the infinite line. Everyone likes that. Nobody likes the periodic case for inverse scattering, right? Infinite line is much easier. So let's start with, we don't want the usual secant squares. We don't want those because they already have poles. We want something where the poles have to be born at infinity. So let's start with this. And let's pick this A, so just a single solid like this, right? So the solution will look something like this, right? Equal to naught. There is your Gaussian, and then sometime later you will have a single soliton. Is it to the right or the left? I'm not sure now. And then you'll have a dispersive tail, right? Now this will look like secant squared, which has a pole of double multiplicity, same as in our case. But initially, there are no poles, right? So I expect in a complex plane that you have a pole born out at infinity, same as in these pictures, and then traveling sort of like that, and end up with this secant squared. So that's my conjecture. I went to the literature and I thought this problem would be solved, but it turns out it's not. I don't think the inverse scattering of this has been worked out.
If you actually rescale your equations about infinity, there are ways by which you would get a similarity form of nonlinear equations.
Okay.
And otherwise you can predict those singularities.
That would be very interesting to see. Okay.
Yeah, I think this potential is just not analytically solvable in terms of inverse scattering, so.
Right.
Need
but
approximate.
anything would be interesting, for me at least.
But I guess you can just see how these poles approach from infinity numerically.
Right. Okay. For those of you who know this history will know that Zabusky and Kruskal did not set out to discover the soliton in that paper. They had a completely different aim in mind. They had this, they were looking for this phenomenon of recurrence. And that dates back to maybe 5 or 6 years before, maybe 10, to a famous experiment by Fermi, Pasta, and Ulam at Los Alamos. Basically, it was a nonlinear system, a lattice equation, a dynamical system that's approximately KDV. And what they observed was, if you start off with, say, like a single Fourier mode as initial condition, nonlinear interactions create higher modes, and those higher modes create more and more higher modes. So there's this cascade of energy from the low modes to the higher modes. But the surprising thing from their experiment was that that doesn't continue indefinitely. They would think the term for that is thermalization. That doesn't happen. The process is reversed. So all that energy at some point flows back, and the initial condition is reconstructed. That is the phenomenon of recurrence. And that was what Zabusky and Kruskal was after, not the discovery of the soliton. So on the left is their picture, and on the right is my picture recreated, of course, with modern tools. But my picture covers a much bigger time domain. So this is time going up that way. This is the space domain. I've stick to their 0, 2 space domain. The colors are the crests of the solitons, so you see the various soliton interactions. For some reason, they didn't start at 0. They started here at 0.1 of the recurrence time and stopped at half the recurrence time. They didn't go all the way to the recurrence, which is bizarre. And I think I have the reason for that, and that is that the recurrence isn't very clear. So in my picture here, we start off with the initial condition. This was like a cos or a sine. So the light blue would be -1 and the dark blue would be +1, or vice versa. Right, this is a modulus plot of the solution. And then they claim that at TR, the recurrence time, you will have recovered the initial condition. So now you have the light blue in the middle and the dark blue at the edges, but you really have to squint your eyes. It's the recurrence is very imperfect in the Zabriskie-Kruskal experiment. I think if they hadn't discovered the soliton in the same paper, this paper would have been rejected because, in my opinion, they didn't really prove the recurrence phenomenon. But what does it have to do with our computations here? But what I thought was, if they were true recurrence, those poles that were coming in along the imaginary axis would have to move back out to reconstruct the initial condition, which is an entire function, right? Or at least, widen the strip of analyticity quite a bit. But I couldn't see that happening. So I think it's simply because the recurrence phenomenon in KDB is not a very strong phenomenon. But if one goes to the NLS, it's a totally different story. Then one can observe it nicely. So NLS, I'm not sure most people are familiar with the Benjamin Fair instability. Here's NLS. I'll keep using this mu as nonlinear parameter. So that has a Fourier mode solution. Let me see. I think that's correct. This is x independent, so the middle term disappears. Take a derivative with respect to t. I think it checks out. A is a complex number. And then if you preserve that by some time and space dependent function, and you do a linear analysis, and you find that the modes plus or minus I in x, this is periodic, they go unstable if n satisfies, I think, something like this. Right, so the bigger your nonlinearity, the more unstable modes you have. And it happens in a very nice and controlled fashion. So if you have one unstable mode, you have like a breather kind of solution. The mode grows, but then at some point it's an integrable system, the conserved quantities kick in, and it subsides, and then the initial condition is reconstructed. So it's a much nicer recurrence than in KDB. If you have two unstable modes, they take turns in dominating. So you have first the one dominating, and then the second one, and then back to the first one, and eventually the initial condition is reconstructed. So I have those also as an animation. And again, I believe that may be the first time that these things have been computed, but I don't know if someone else knows about it. About other computations, please let me know. This is a different animation, different style of animation. I wasn't sure if, well, in Ekiam there were no MATLAB on their machines, so I converted it all to PDF. And so I animate by keeping my finger on the arrow. So, oops, this one's, I'm running it in reverse now. how do I go to the beginning? There must be a way, right?
So this is the Benjamin Fair model, right?
Sorry? Yeah, this is the Benjamin Fair instability. With the first I'll show you one with just a single unstable mode. So it's just
if the conditions start from one unstable mode.
it's I should have said well, we're perturbing that. This is where the
Yeah, of course.
yeah,
there is.
we're perturbing,
Yes,
so
plus
t equal to
perturbation.
naught. We're starting with a uniform solution. I forgot what the A was in this particular case. Yeah. So in the upper figure, now the modulus is plotted, right? This is a complex valued function. So yeah, here the poles come. Here I plot both upper and lower half planes because complex valued function is no up-down symmetry. So this is the lower half plane, that's the upper half. Actually, I like this kind of animation because you can stop anytime you like and just check out. Right, and right there we are roughly back at the first. I should have said you don't. Normally, your first recurrence is just off by a phase shift, so it's a different color than when we started off, right? Just the opposite phase. And then when you keep going, there we're back to the red color that we started off with, which is the same phase as the initial. It's interesting, if you look at the zeros, they run right through the real axis. But the poles bump off of each other. So yeah, I thought this was a nice picture. And then in the next one I will show is the case where we have two of those unstable modes. So it's not just a single hump, but a single hump and a double hump alternating.
So are there any branch cuts associated with the zeros?
Not as far as I know. With the zeros. Not as far as I know.
So the fact that the zeros do run through the real line doesn't imply singularity.
No. Yeah, so, oops, why again? How do I get to the start? Is this? Nope. Hey, oh, there you go.
Escape.
No, it looks like I'm at the start now. T equal to 0, right, okay. Starting with the same initial condition. There you go, oops, that's too fast. Let me backtrack a little bit. So there's the first hump, the first mode dominating. So that's controlled by the two poles nearest, on the imaginary axis, nearest to the origin. But then you see these two others appearing also as part of the Benjamin Fair stability. And then when they become dominant, you have the two-hump solution up there. And then, yeah, the process goes on like that. Right, and if you make the nonlinearity even bigger, well, you can have another pair of unstable modes, which I haven't done, but which will presumably have more sets of poles. There you go. Okay, the one nonlinear feature that I haven't talked about is nonlinear blow-up. And as I said before, with adding diffusion or dispersion, you won't get blow-up in these problems. However, if you start with if you just change your real initial condition to complex, you can get blow-up, which I found surprising the first time I realized this. I did these computations. So this is now the same burgers as before, but with the complex initial condition. Again, I show both upper and lower half planes because there's no symmetry, because it's our complex value solution. And you see the poles entering from above as before. That's why I put the minus in front of the I, otherwise they come from the bottom, so just easier to see if they come from the top. And then at a certain time, you get the blow up. And it's like, if you do this by the dynamical system approach, it's like there's no pull from the bottom to keep the upper one in check, right? So it just runs right through the origin and it blows up. Marco and I have been looking at this, at that particular problem, analyzing the integral with the Hopf-Kohl transformation. And so we have a fairly good handle on when blow-up happens and when it doesn't. For example, if nu is too large, then you still have the turnaround thing before the blow-up occurs. Here is the Zabusky-Kruskal experiment. So the same choice of the coefficient in the Zabusky-Kruskal experiment, except that simple change was made to change the original function from the sine to the complex Fourier mode. And then also, again, you have the poles drifting off into the left half plane, but then it also blows up. Afterwards, we discovered papers where this was discussed in KDB and in Burgers. And just when I did it the first time numerically, I was quite surprised. I didn't expect this. The rest of this talk is about the numerics, but since we are about at the end of the 15 minutes, I'm just going to give you one slide of numerics, and just to tell you how this, and I think I've already said this, the equations were solved by Fourier spectral method, method of lines, so we integrated on the coefficients. To see these things, you really have to crank the accuracy on the time integration quite low, otherwise you don't see it. And you have to take quite a number of Fourier modes. If you know that your solution just consists of poles, then you can use the Fourier Pardee approach, which is what I've used in the stuff that I showed you. There's a new method by Nick Trefethen and Yuji Nakatsukasa and Olivier Sept, which is very different from Fourier Pardee. It's based on the barycentric formula for trigonometric interpolation. And it seems to be promising, but I need to do more experiments to really say which of these methods work the best for this particular case of moving into the complex plane. And then if you have multi-valued solutions, well, none of these can capture branch point information. So in order to put to get some branch structure in your approximation, you have to go to something like quadratic Pardee, which is what we've done. We've solved the, maybe I can show you just very briefly one picture. This is back to our Inverse-Burgers equation where there's a branch point singularity. This middle picture is what the Newton iteration that I described right in the beginning gives. The branch point coming from along the imaginary axis. If you do it with Pardee, you get a meromorphic solution. What happens is that the poles of that meromorphic solution are put right where the branch code is. So it's as if Pardee uses the sequence of poles and zeros as a proxy for the jump in phase. That's well-known stuff in approximation theory for regular Pardee, but it also happens in linear Pardee. So that's pretty much useless in terms of numerical computation. If your interest is this kind of behavior. If you go to quadratic Pardee, which I haven't described, but if you're interested, we can talk about that. If you go to quadratic Pardee, you get an almost perfect reconstruction.
Can you define only the location or also the nature of the branch point?
Well, your approximant is quadratic. So it sort of can give you the jump in phase, but it will not tell you the exact type of singularity. Of course, you can go to cubic and higher type Pardee approximants, but my experience with those are limited. Okay, thank you very much.